Hello and welcome everybody to my talk, which is based on a joint work with Sten Andreas Bethusen, Matthias Birkner and Timo Schlüter. And the paper with this title here can be found on arXiv under this link. So let me first explain the model. So the oriented percolation on ZD times that here we have IID random variables at each site, which are Bernoulli distributed with parameter p. And being 1 is interpreted as being open, and being 0 is interpreted as being closed for this site. And we say that we can reach xn from ym if there is an open path which connects these two sides, and the path is allowed only to take steps of size less or equal to 1. So it goes up, like in this picture. The blue is the open path starting in this one side. So the well-known fact about oriented percolation is that there is a critical probability PC, so that in the supercritical case, in the case P larger than PC, the percolation probability of one side is positive. So the probability that there is an infinite open path going up from the side 0, 0 is positive. We will assume only, we will consider only the case P larger than PC. And okay, we define the cluster of percolating sites denoted by calligraphic C as the sites in ZD times Z which have an infinite open path starting in them. Yes. Assume that we know for some reasons that these red points are connected to infinity. Then we can, from time slice to time slice, color the other sides as red or not. So in this, yes, I hope this is clear how it is going. So if this side is connected to, I hope that you can see this. If the upper left red side is connected to infinity, then the one below red is also connected to infinity, which was gray before. And the property of the side percolating sides of this cluster is that if I know that a side is connected to plus infinity, then of course there is a side in front of it in the upper time slice which is connected to infinity as well. Okay, on this cluster we can define a random walk. Here it is in blue, a random walk with possible path in blue, so that it takes only steps on the sides from the cluster, and it is clear that if I start on the cluster, then I can always choose uniformly one point from the cluster in the upper time slice. But what can be seen here already is that this random walk is not elliptic. So the probabilities are not elliptic because, for example, in the second step, I can only choose one side from the cluster C, but not the others. Okay. And one other property of this cluster is that we know we started off with gray colors, which were assigned in IID manner, but the red dots, which are read off from the gray ones, they are dependent. So for example, in this configuration, if we know we start with 3 gray sides in a row, and for some reasons we know that the first one is gray, the second one is red, then it implies that the third one must be red as well. Okay. Here's a formal definition of the random walk starting on the cluster. So we assume that the point 0, 0 is in the cluster, and then the random walk does the following. So we start in 0, 0, and then, yeah, here it is written, you choose if the random walk is in X at time N, then we choose uniformly one of the points in the time slice N plus 1, and we choose uniformly from the neighborhood intersected with the cluster. Okay, this random walk can be interpreted as a direct random walk on this random graph, but it can also be interpreted as a random walk in dynamical random environment generated by a reversal of a contact process. Okay, I leave this interpretation open here, and this can be found in this paper by myself with Matthias Birkner, Jerzy Czerny, and Nina Ganter. In that paper, we have proven the law of large numbers, annealed and quenched, which are equivalent, and we also have proven the central limit theorem in the annealed and quenched versions. Here it is not the case that they are equivalent, so the assertion 2 is stronger than 1. And this was proven for all dimensions larger than 1, spatial dimensions. So we have a spatial dimension D, and the time dimension is 1. Okay, then it is clear we can't consider such random walks without conditioning on this event B. We just let the walk evolve at the random walk, which takes uniform steps, and at some point it will hit the cluster after some time which has exponential decaying tails. And okay, therefore these results do also hold without conditioning on B. What we are interested in are the random local limit theorems for this random walk. In the literature, there are some local limit theorems in random media. We have discussed them in the paper. But the main inspiration, or the main source, the main ideas are in this paper, which we have used by Berger, Cohen, and Rosenthal. And they have proved a local limit theorem for a random walk in a random environment. And their assumptions are the following. So the random walk is ballistic. The dimensions are larger than 4. And this is also in our case. We are also able only to handle dimensions larger than 4. We have 3 spatial dimensions and 1 for the time. The uniform ellipticity is something that we don't have, and IID property is also something that is not true in our case. Okay, let me just show you the results. So the first result is the annealed local CLT. Here we have convergence to Gaussian. So this is a d-dimensional Gaussian density with the same covariance matrix as before in these results. And the proof here uses a triangle inequality and annealed derivative estimates, which were obtained by Sebastian Steiber for this random walk, and also the annealed CLT. And the main result is the quenched local limit theorem. Here we also need the 3 spatial dimensions and the time dimension. And then there is a unique measure Q, which is absolutely continuous with respect to P, and invariant with respect to the point of view of the particle. then for the radon-nickel derivative of this measure Q with respect to P, we have for almost all omegas that, yes, this sum converges to 0 as n goes to infinity. And this is the quenched local limit theorem. So we have here the quenched law, we have here the annealed law, and the annealed law is reweighted by the radon-nickel derivative of Q with respect to P. And okay, and I haven't written what sigma is, but sigma is the shift operator which shifts the environment so that xn becomes the new origin. Okay. Here, let me say 2 words more. So here, this law is not aware, the annealed law is not aware of the environment because this is averaged over all the environments. And this quenched law, for each omega, there are some points x at time n which cannot be reached by the random walk, so that this probability is 0. So it is clear that some reweighting which takes account of the environment is needed. And the nice fact here is that this reweight is by this radon-nickel derivative. Okay, let me stop here. Thank you for your attention.